All right, y'all. This is picking up with chapter 7, membrane structure and function. You guys know that the cell membrane works as a perfect semi-permeable boundary for cells because of the nature of the phospholipids, polar heads, nonpolar fatty acid tails, and proteins. Two main components of the plasma membrane. There are some carbohydrates, there's some cholesterol, there's some other stuff that you can see in the slides, but these are my two favorites, and I think they're the most important. Plasma membrane maintains homeostasis by regulating what gets in and out of the cells. So here you got this boundary of a living thing and a non-living thing. You gotta have some skills at controlling how things move across that boundary. And then the third thing plasma membrane does is play a real important function in cell signaling. This would be like signal transduction pathways with ligands. So signal transduction pathways always allow cells to respond to changes in their environment, to signals from other cells, and more on that when we get to chapter 11. Right now we're in chapter 7. Good job. Now, how do cells transport stuff across membranes? Well, the easiest is simple diffusion. This is going to be with things like O2, CO2. What do they have in common? They are non-polar. And, boys and girls, you got it, small. Now, Jude's looking at me. Actually, you guys know him as Jude. He looking at me like, that voice is annoying, Mom. And he actually told me a few minutes ago, he said, I think your students don't like it. I think it's annoying to them too. And I think they're just telling you they like it. So, I don't know, maybe Jude's right, and maybe this is the last time you hear this version of my teaching. But, back to the point, oxygen, carbon dioxide, what are they? Small and nonpolar. They cross the membrane directly. High to low concentration, no energy required. Facilitated diffusion, you can't cross the membrane directly. Why can't you? Because you're charged. You're an ion. Okay? Or you're big and polar, like glucose or sucrose, okay? Not going to get across the membrane directly. Going to have to go through a protein channel. Guess what? No energy required. Why? High, low concentration, boys and girls. All right, finally, we got active transport. Active transport is either... Wait, 1 second here. Active transport always requires energy. Now, it's either going to be from low to high, like we're pumping it in. Got 5 dogs, remember that? Or it's going to be endo or exocytosis. Okay, movement of large amounts of material by fusing vesicles with the membrane, stuff like that. Now, the one thing that stands out of this unit that tends to be the hardest is this. I'm going to change colors just for emphasis. Water, a simple, small, yet polar molecule, moves through the membrane by facilitated diffusion. And the cell can't do much about water because it's always around. So water moves by facilitated diffusion through protein channels called aquaporins. But here's the thing about water. It's always there. So it gets a special name because cells are always dealing with it and stuff. The special name it gets is osmosis. Osmosis is the facilitated diffusion of water, boys and girls. And to elaborate on that a little bit, I got this page for you. It's a big topic. I'm not sure if it's going to show up, but likely to show up. Got 3 cells. I had 5 dogs, now I got 3 cells. I got one in a hypotonic environment, because the concentration of solutes in this environment is less than that of the cell. I got another cell in an isotonic environment, and then I got a third cell in a hypertonic environment. These are all concentration of solutes in the environment, okay? So it's hypotonic because there's less solute, hypertonic because there's more solute in the environment, isotonic because it's the same. You guys know what's going to happen here. Water goes in, water goes out. Cell maintains its, water content. Not that big a deal. But in this environment, what's going to happen? Well, water's going to have to go in. Why? Well, you can say this like a freshman, or you can say this like an AP scholar, and I think I know which one you are. Water goes in because water always moves towards an area of lower water potential, meaning the water potential of the cell is less than the water potential of the environment. Why is that? Well, water potential gets more negative as we increase the solute concentration. Okay? So the water potential in the cell is going to be more negative. And being more negative, it's going to cause water from a less negative water potential to be moving from an area of high to low water potential. So this is going to be higher water potential, lower water potential. They're both negative numbers because the water potential of pure water, folks, it's always 0. So you never have positive water potential, only negative water potentials. Pure water is going to be 0. This is not pure water, it's 1% solutes. This is not pure water, of course, 3% solutes. More water on the outside going to come in. But the way you describe that, because now you're a scholar, practically almost doctors, and whatever you want, is that the water potential in the cell is more negative or less than the water potential of the environment, causing water to move in. Opposite's true over here, right? So here, the water potential in the cell is going to be greater than the water potential of the environment, which means water's got to leave. Water always goes to where the solute concentration is higher. Don't screw that up. The solute concentration's higher, but the water potential's lower because it's more negative. Now, to be honest, I don't think you're going to have to calculate this shit. Oh, excuse me, I didn't mean to say that. I don't think you're going to have to calculate it on the exam. I think you may just have to interpret the values. So here we go. Water always, here's Jude with me, moves to an area of lower water potential, which means the more negative value.
That sound is cringy.
What sound is cringy, Jude?
The sound of the marker.
Jude doesn't like the sound of writing utensils on paper. I think maybe he just doesn't like school, but
That's untrue.
he said that's untrue. You want to say anything else, Jude, before we sign off?
No.
Okay, I got one more thing to say, though, y'all. Organisms, and Jude, can you please excuse me, please?
No.
Organisms have the ability to regulate these situations. So sometimes it's referred to as osmoregulation. And what I mean by that is if a cell is in a hypertonic environment, there's usually like sugar water or salt water. If a cell's in a hypertonic environment, it may release more solutes into its cytosol so that it loses less water. Does that make sense?
No.
Or if a cell's in a hypotonic environment, it may remove solutes from its cytosol so that it gains less water. So cells have these mechanisms to, especially those living in watery, like aquatic, of course, environments, they have ways to deal with it. More on graphs in the next video, because you guys need to understand what the graphs look like for these experiments, you know, where they make a dialysis tubing bag and put stuff in it and put stuff in the environment, and you know how that is because we did it. But miss you guys, and thanks for watching. And Jude, you want to say anything else? He said no. All right, back to Jude's homework, y'all. Have a good day.